Energy, it's the pulse of life. It's what makes the world go round and round. Energy, it joins everything from the sun above to oil underground. Fossil fuels a gift that is stored underground. We're burning it up, someday no more will be found. And in the atmosphere we are creating a mess. We've got to learn to be much smarter with less. Efficiency is a must before the planet goes bust. Energy, it's the pulse of life. It's what makes the world go round and round. Round and round. Round and round. Round and round. Energy.
We take for granted the energy that powers our modern way of life. As we have raised our standard of living, we have dramatically increased our consumption of energy. North Americans have the highest per capita rate of energy use, making us the biggest energy spenders the world has ever seen. Can we afford to keep spending energy at this rate? What other energy choices do we have? First, let's look back. For most of human history, the only source of mechanical energy was muscle power. Ingenious devices were invented to convert this limited energy into work. For short periods, an adult male can generate about 200 watts of power, but can only sustain about 100 watts. A typical horse can produce about 750 watts, which is therefore equivalent to about 1 horsepower. About 2,000 years ago, we began to use the first energy-generating machine, the water wheel. Its energy ultimately comes from the sun, which re-elevates the downstream water through evaporation and rain. A typical water wheel in the Middle Ages produced about 3 horsepower and never had to be rested or fed. About 1,000 years ago, humans began tapping another source of solar energy. Early windmills were low to the ground and pivoted on a central post so the whole structure could be rotated into the wind. Later windmills were higher and therefore closer to the wind. These tower mills pivoted at the top and could automatically turn into the wind. The power output of a large 18th century windmill was as high as 16 horsepower. However, being at the mercy of the weather, a windmill can't guarantee energy whenever it's needed. Neither, for that matter, can most water wheels. And since both are limited to certain locations, they can't always provide energy wherever it is needed. However, heat is an energy form that can be produced anywhere, anytime. So the next step was to build a machine to convert the heat of a fire into work. The first such machine was the steam engine, but it took several tries to get it right. The first steam engine was patented in 1698 by Thomas Savery, a retired English army captain. Its purpose was to pump up water from the bottom of mine shafts. First, steam was produced in a boiler. It then traveled through a valve and into an empty chamber. After the valve was closed, the chamber became airtight. As the steam cooled and condensed into water, a vacuum was formed. Atmospheric pressure would then push water up the mine shaft and into the vacuum. The valve would reopen, allowing in a new batch of steam, which would drive the water out, and a new cycle would begin. The Savery engine was slow and cumbersome, with a maximum output of about 1 horsepower. It never really succeeded in the task for which it was designed. 14 years later, another Englishman, Thomas Newcomen, came up with an atmospheric steam engine that actually could keep a mine shaft dry. As this transparent model shows, its vacuum is formed in a cylinder and pulls down an overhead piston. However, Newcomen's real breakthrough was to speed up the condensation of the steam by spraying cold water into the cylinder. The up and down motion of the piston was transmitted to one end of a rocking beam, the other end of which powered a suction pump, to lift water up and out of the mine shaft. The Newcomen engine could generate about 5 horsepower, but was terribly inefficient. Less than 1% of the energy of its fuel was converted into work. In 1765, a self-taught Scottish engineer, James Watt, thought of a far more efficient way to condense steam. This is how he did it. At the end of each stroke, a suction pump drew the steam out of the cylinder and into a separate chamber, which was surrounded by cold water. This is where the steam condensed and formed a vacuum to pull down the piston. Watt's engine allowed the cylinder to remain hot at all times and avoided the energy expense of reheating it with each stroke. As a result of this gain in efficiency, his engine was more powerful than Newcomen's, while using only a fraction of the fuel. This ingenious innovation revolutionized our ability to harness energy for work.
In 1698, Captain Savory had a notion to transform heat into some kind of motion. The first steam engine was a great big clinker. It didn't pour steam, it was more of a steam shrinker. Each time the steam went to cooler from hotter, vacuum was formed which could suck up water. Thomas Newcomen learned how to cool steam faster. The wasted heat was an efficiency disaster. James Watt thought if you took steam away, you could manage to avoid this whole cooling off delay. Removing and condensing it was his solution. It worked so well it caused the Industrial Revolution.
The Industrial Revolution, powered by steam, led to an explosion in energy use. Later steam engines used more efficient high-pressure steam rather than atmospheric pressure to drive the piston. This 19th century steam engine powers an entire factory through a connecting belt, which turns an overhead drive shaft, which in turn drives the machines. It was an awkward system, but it worked. Mass production began in earnest, and the use of coal skyrocketed. The steam engine became powerful enough that a compact version could be mounted on wheels and propel itself. But the steam engine, too, had its limitations. Each location had to have its own machine, which was noisy and dirty. Then there was the inconvenience of transporting and storing the coal. What's more, steam engines were not terribly versatile. They could produce mechanical work, but not heat or light. By the mid-19th century, scientists were well aware of electricity and how to generate it. But it was little more than a curiosity until 1879, when in this lab in Menlo Park, New Jersey, a new electrically powered light source was developed. Thomas Edison was the first to see the potential of electricity to provide people with new services like clean, safe indoor lighting. But in order to provide these services, he also had to provide the electricity, which he did. Within 3 years, Edison had built the first electrical distribution systems, wiring whole communities to Edison electrical generating stations like this one in Detroit. Soon, the electric motor made possible other new energy services like the streetcar. All kinds of newfangled devices blossomed forth. More efficient turbine generators, including hydro-driven ones, replaced the old steam pistons. Barely 100 years after the steam engine, electricity had brought about a second energy revolution and another steep increase in our energy use. The third modern energy revolution, that of the gasoline-powered internal combustion engine, arrived within a mere 2 decades. Electricity speeded it along, powering the new automobile assembly lines. Motorized travel was now freed of railway tracks and electrical lines. Individual energy use exploded yet again. How long can we maintain this ever upward trend in energy use? Energy supply is not the pressing issue it once was, although fossil fuels are a finite resource and will not last forever. What will be depleted long before then is the capacity of the environment to safely absorb the effects of this much energy use. The fossil fuels, oil, coal, and natural gas, together provide about 80% of our energy. About half of that energy comes from oil alone. Its popularity, especially for transportation, is easy to understand. It is a portable fuel that packs a lot of energy into a small space. To varying degrees, the fossil fuels share the same environmental problems. Getting them out of the ground can cause damage. So can transporting them. But their most serious effects occur when they are burned and release the oxides of sulfur, nitrogen, and carbon into the air. In the case of sulfur dioxide, which reacts with water to form acid rain, coal is the worst culprit. Oxides of nitrogen, a major ingredient of smog, are mainly the result of the oil products we burn in motor vehicles. Carbon dioxide is potentially the most troublesome pollutant of all. Coal, with the highest ratio of carbon to hydrogen, produces the most CO2 per unit of energy. Oil comes next, and natural gas, which contains 4 times more hydrogen than carbon, puts out the least of all. Carbon dioxide is critical because of its effect on global climate. When light from the sun penetrates the atmosphere, it is absorbed by the Earth and emitted back as infrared radiation. Some of this radiant heat is then absorbed and reflected back by certain gases in the atmosphere, trapping it there in the same way that a greenhouse traps heat. Some of these greenhouse gases are also produced by our use of fossil fuels. The most important such gas is CO2, which alone accounts for over half of the greenhouse effect. The dramatic increase in our use of fossil fuels over the past 200 years has brought with it an increase in the concentration of CO2 and other greenhouse gases in the atmosphere.
The increase of CO2 has been over pre-industrial levels, has been around 20 or 25%. Other greenhouse gases have increased, in many cases even more than that. And so there's no question that man's industrial activities have increased the greenhouse gas concentration in the atmosphere by a significant amount.
There's a very high degree of consensus that we are conducting this uncontrolled experiment on the atmosphere, which is going to have effects. The exact nature and location of those effects there's more uncertainty about, but there's little doubt that, that we're going to experience global climate change if we keep pumping out the material we are now pumping out into the atmosphere.
The major risk is that the increase in CO2 and the other greenhouse gases will cause the atmosphere to heat up. What will this mean to life on Earth? The answer is not yet clear, but the potential for disaster is real.
But overall, for the world, for the globe, we are already at record high levels of temperature averaged across the whole globe, and the continued production of greenhouse gases has the potential to drive us well beyond anything that has been experienced in the last 1,000,000 years.
What about alternatives to fossil fuels, like hydropower? In water-rich Canada, hydro generates over half of all electricity. It's an emission-free, renewable, and cheap source of power, but it comes with its own environmental price tag. Damming a major river floods out large areas of plant and wildlife, as well as dislocating the local communities. In addition, these man-made lakes sometimes leach poisonous mercury out of the land and into the water, where it gets into the marine food chain. Hydro-generating sites are usually remote and require long transmission lines which cause damage of their own to the landscape. The other major option is nuclear. It too creates no air pollution, but again, there are other environmental costs. Uranium mining is dangerous and leaves behind radioactive tailings. The reactor itself is a complex, expensive system which is prone to technical problems. As well, the leftover fuel is highly radioactive and presents a long-term storage problem which hasn't yet been solved.
Fill her up, bell Joe, I'm feeling footloose and free. Gonna fill my tank with that petrol energy. Oil, coal, natural gas, let's burn them up now while they last. After all, isn't that the path to prosperity? Prosperity. But now these fossil fuels have shown up in our skies, into which carbon, sulfur, and nitrogen all oxidize. Our thermometer's starting to gain, there's acid falling down in the rain. Our energy habits and nature just don't harmonize. What about those other ways to get electrical kicks? Like waterfalls, uranium rods, or just burning sticks. Nuclear has caused a clamor. Is hydropower worth a damn? Or is there some other way to get out of this energy fix? Yeah! How we gonna lick those energy blues? We gotta lick those energy blues. I said we gotta lick those energy blues. How we gonna lick those energy blues? Energy, it's the pulse of life. It's what makes the world go round and round. Energy, the single theme of life that weaves everything into common ground. Energy, it's the pulse of life. It's what makes the world go